Hello and good afternoon. My name is Tahlil, and my project primarily focuses on two materials, potassium tartrate hemihydrate and potassium bitartrate as potential electron paramagnetic resonance dosimeters for low-dose radiotherapy cases. Now, in modern cancer treatment, radiotherapy plays a major role. It's used in about 50% of all cancer treatments and makes up about 40% of all curative treatments. Now, ensuring a precise dose delivery of radiation to the patient is also of utmost importance because even a 5% dose error compared to the planned dose can cause the tumor control to go down by 10 to 20%, as well as increased risks of other consequences such as radiation-induced bone fractures and secondary malignancies. Now, these dose errors can arise due to very minute reasons, such as changes in the breathing motion of the patient, as well as changes in the anatomy of the patient between treatment sessions. Now, these dose errors become even more consequential in the case of fractionated radiotherapy, where patients are subjected to 1 to 3 grays of radiation over the period per day over the period of their entire treatment session. Now, with the ability to detect radiation-induced free radicals, electron paramagnetic resonance dosimeters give us a new, more sensitive method to carry out the verification of the doses delivered to these patients. Now, how the EPR functions is that it primarily detects, again, radiation-induced free radicals, which are produced when a material absorbs ionizing radiation. What the EPR then does is that it subjects the material to a magnetic field as well as microwave radiation, which the material then absorbs at a characteristic frequency. Now, this then produces the EPR signal, whose intensity is directly proportional and correlates with the concentration of the free radicals that are produced in the material, which in and of itself is directly proportional and correlates with the amount of dose of radiation that the material has absorbed. Now, conventional EPR dosimeters, such as alanine, have a very low sensitivity below 5 gray, which make them not very suitable in fractionated radiotherapy dose ranges. As such, within the context of this study, we look at two materials, potassium bitartrate and potassium tartrate hemihydrate, which have been studied before and show a lot of promise in these to detect radiation in these dose ranges. Now, in the context of this study, we carry out the dose response on these two materials over a range of 1 to 10 gray. We look at the signal stability of the material over a period of 44 days, as well as what we see here is the cumulative dose response of the materials when they are subjected to fractionated doses of 2 gray per day over a period of 4 days, so totaling 8 grays of radiation. Now, this last part has never been done in any previous studies that focuses on these two materials. Now that we have the background out of the way, let's look at how we actually carried out the study. Now, both of these two materials, potassium bitartrate and potassium tartrate hemihydrate, were used without any form of chemical or physical treatment after they were purchased from the supplier. They were then weighted and sealed into polythene bags to be subjected to irradiation. Now, the samples were divided into two sets. One set of the samples was irradiated with 1, 2, 4, 6, 8, and 10 grays of radiation, single doses of radiation, whereas the second set of the samples were irradiated with fractionated doses. They were given 2 grays of radiation per day over a period of 4 days. Now, this was done to stimulate a fractionated radiotherapy session over a period of 1 week. So after the irradiation, these samples were then transferred to EPR sample tubes, which were then placed inside the EPR spectrometer and the EPR signals were then obtained by using the parameters given in this poster. Afterwards, after the signals were obtained, they were then analyzed using the JEO ESR DP that was provided to us by Nuclear Malaysia, as well as Excel and Python to carry out further analysis of the materials, which primarily focused on looking at the peak-to-peak height of the material or the signal intensity, as was previously discussed. Now that we have the methodology out of the way, let's look at the results that we obtained throughout this study. Now, as you can see in the first graph, in graph A, PT compared to both alanine and potassium bitartrate, our other sample, showed the highest level of sensitivity, which again was consistent with the results that were obtained in previous studies that were conducted on potassium tartrate hemihydrate. PB, on the other hand, potassium bitartrate, showed a much lower sensitivity compared to PT and alanine, which again does agree with previous study that was conducted on the material. Now, if you look at figure B, which looked at the cumulative dose response of the material, potassium tartrate again shows a linear dose response with increasing dose, even in the cumulative dose response. It has a deviation, if it was compared to the dose response as a reference, it has a deviation of about 10.3%, lower than 10.3%. PB, on the other hand, a potassium bitartrate, shows a very sharp drop after 2 grays and then becomes linear and shows a positive linear dose response after 4 gray with a maximum deviation of about 30.9%. And then we looked at the stability of the two materials, how the signal changes over a period of 44 days. Now, in figure C, as we can see, potassium tartrate hemihydrate drops to about 70% over a period of 44 days, which is similar to the 35% drop that was seen in the previous studies conducted on it. PB, on the other hand, shows a very sharp drop within the first 5 days of analyzing the signal stability, and then remains completely stable over the period of 44 days. Now, this very sharp drop in the 5 gray can also be used to explain the very sharp drop that we see in the cumulative dose response. After that, since the stability remains stable, the signal remains stable, the cumulative dose response again shows a positive linear dose response as well. As such, with the results in mind, both of these two materials actually do show potential to be used in fractionated low-dose radiotherapy sessions. PT due to its very high sensitivity in low doses, PB due to its exceptional signal stability over a period of a very long time. Now, obviously, further research will be needed to refine the performance of these two materials and actually validate them in clinical conditions. But again, what we hope through this study is that this study highlights their strong potential for real-world applications in radiation therapy and actually be able to verify the doses that are given to patients and get rid of a lot of these consequences that come from the dose errors. As such, improve the quality of care delivered to patients, as well as potentially be able to help save lives. And with that, thank you very much for listening to my presentation. Hope you have a lovely day ahead of you. Thank you very much.